Okay, we were discussing about this timing diagrams in the last class. So you've seen that how the code is fetched, decoded, and executed by the processor. Okay, so we have taken an example in which we have moved the contents of accumulator into C, right? So we have discussed how the various control signals they are generated and activated by the processor in a sequence. Okay, so this is one byte instruction. So this entire operation is basically executed using a single byte. Okay, or in the opcode fetch cycle itself the instruction gets executed. Now we will take one more case where you have opcode fetch along with the memory read cycle. Okay, opcode fetch plus memory read, so it must be a 2-byte instruction, right? So let us suppose I take example mvi a comma 32h. Okay, so this is a 2-byte instruction because you have to load a number 32 into accumulator. So for that, you for the first, of course, code is always a operation code. So for the instruction the code is suppose 3eh, and it will be stored some at memory location. Suppose it is stored as a memory location 2000h. So the next byte will be stored at 2001h. Okay, so 3e is opcode and 32h is now data byte. Okay, so the processor will first fetch 3 from this location. It will decode it. It will come to know that it has to move a number into accumulator A. So then it will get the next cycle, which is the memory read cycle. It will get that number from memory and place that data in the accumulator. Okay, now you see using the timing diagrams how it is done and how many clock cycles will be required. Okay, now of course the first cycle is the opcode fetch, and you know we need 4 T states for that, 4 clock cycles. Okay, but just to make it clear, I am just revising it again, and then we will combine it with the memory read cycle. Okay, so we have different clock signals here again. So okay, so in many books you will see a clock is represented like this. In some of the books they also denote it like this. Okay, so it is basically ideal case. This is not the practical clock signal that we get, because it needs some time to go from level 0 to level 1, of course. Okay, so there is some rising time, some falling time. So it is the ideal case where it goes from 0 to 1 abruptly, which is not practical. Okay, so anyway, it does not matter. So you have different clocks. I have now denoted again different clock cycles here. This is 1 clock period. Okay, so I'm writing these diagrams so that it becomes, sorry, this I have taken wrong, so that we get more clear concept. Otherwise I could just have taken a snapshot from the book and explained it, but using this you will get a more clear picture. Basically you will be able to draw any time diagrams if you know the sequence of control signals which are activated by the processor. Okay, so your different clock cycles, which we call as now T states. Okay, so this is T1, this is T2, T3, T4, T5, T6, T7, T8, of course, which is not used. So you have 4 clock signals, 4 clock periods. You know, now the first part is opcode fetch, and it requires 40 states. Okay, so this you already know, but just I'm repeating it so that you again get it revised. So what the processor now does in the opcode fetch cycle, it will first fetch the opcode and it will decode it, and it will come to know what has to be done. Okay, and for that What has to be done? You have to first place the address on the address bus, that is A8 to A15, higher 8 bits, and this address remains on this for almost 3 clock periods, and then it is unspecified in the last period. Okay. Similarly, your lower 8 bits AD0 to AD7, the lower 8 bit address, that is now, see, I'm using this. First I'm fetching the opcode, that is 2000H. Okay. So it means 20H is placed on this bus, and on your lower 8 bits you place the second address, that is 00H. Okay. So lower 8 bit address 00H will be placed on the lower 8 bits, and at the same time in the first clock period itself the processor will activate this ALE signal. It goes from high to low to high for a small period of time, during which this lower 8 bit address is latched. Okay, and for next cycle now they are free to carry data, right? And at the same time you have status signals, you have IO oblique memory. Since it is opcode fetches a read operation, memory related operation, so it will go from logic 1 to logic 0. Okay, and then you generate a control signal, that is read. So this has to be activated in the second clock period, because in the first clock period the processor is busy in latching the lower 8 bit address. Okay, so once it has latched this lower 8 bit address, in the second clock period the processor will activate a read signal which stays at logic 0 for almost 2 periods before it is again set to 1 by the processor. And during now this clock, during these two states, the data, that is 3H, which is the opcode, it is basically placed on this data bus. Okay, now this is placed on the data bus, and during the T4, now see, it is a 2 byte instruction. It means it will be not executed using the opcode fetch cycle only. Okay, the previous case that we have taken, it was a single byte instruction in which the entire instruction was executed in a opcode fetch cycle only. But since you have to now load the constant number, that is 32H, into the register A, it means in the T4, state, or the T4 or fourth clock time period, the processor will understand this instruction. It will decode, basically not execute now. Okay, it will decode and it will come to know that okay, now it has to load a constant number into the accumulator, and that number is stored at the next memory location, that is 2001. Okay, so once this processor has placed the address on this address bus, the program counter is now free. Okay, it has been incremented by 1, so it now points to the next memory location, that is 2001. Okay, now what will happen in the T5? Now the second cycle will start from T5, which is now memory read. It means in this case the processor has to read a data from the memory, and it has to place this data in the accumulator. Okay, so again the process is same. What the processor will do, it will again first place the higher order address on the higher order 8 bits, that is now the address is again 20, of course. On the lower 8 bits it will place the lower address, that is now 01H. Okay, and this ALE will be again activated. It will again go from 0 to 1 during T5 clocks cycle, and this input output oblique memory, it will, of course, it will remain at logic 0 because it is again a memory read operation. And this read signal will be activated now in the T6 state, because during the T5 clock period the processor is again busy in latching the lower 8 bit address. Okay, so this of course will remain on this for entire time period, for entire 3 cycles, higher order address. But the lower order address 01H, it is latched in the first clock period of this cycle, that is T5, using the ALE signal. So the processor will activate this signal ALE, and this lower 8-bit data is last. Now in the next part, this is free to carry the data. Okay. So what the processor will now do, at the start of this T6, it will again generate a control signal, that is read. Okay. So it was at level 1 now. So initially during the opcode fetch, the processor has activated this signal here at the start of T2, the second clock period, and then it is again set to 1. Okay, it goes from 1 to 0, then again back to 1, because every time it has to be read operation, it has to be activated. It cannot stay on 0, okay, for the entire time period. So once it goes from 1 to 0, so one memory read operation will take place. Then it will remain at logic 1. So if you have to do another operation, it will has to again go from 1 to 0, so that it goes here in the T6 T state. It again goes from logic 1 to 0. And now what is the data on this? Now it is not a opcode fetch cycle, it is a memory read cycle. So the data 32H will be now placed on the data bus during this time. Okay. And in this T3 only, T7 in fact, in the third clock period itself, this data will be placed inside the accumulator. So you need not now this T8 next clock cycle is basically not required here now. Okay, so you need only three machines and three T states to complete this machine cycle, that is memory read. Okay, so in the first cycle, so what we have done in the first cycle, we have placed the higher and the lower order address on the address bus. At the same time, the processor has activated the ALE signal, so the lower 8 bits they are latched. Okay, and in the next clock period, next cycle, the processor will generate a control signal, that is memory read. So whatever is the data inside that memory location, it comes on the data bus. So from the data bus, the processor already know, okay, what is it has to do with the data, because it has been decoded in the earlier cycle, that is opcode fetch. Okay, so it has to already understands that, okay, whatever the data is coming from the memory in the next cycle, that has to be transferred to a accumulator. Okay, so for that you do not need an extra machine cycle. So that is why in the machine write cycle we have only three states. Okay, there is nothing like instruction. It is only fetching part, basically memory read part. There is no decoding and executing now. Okay, the decoding and executing has been done in the T4 itself. Okay, the processor has already understand that whatever is the second data byte that you are coming from the memory, it is a data byte and that has to be gone to accumulator. Okay, so all that is done in the two states only, T6 and T7. Okay, so this is your memory read operation. Okay, so opcode fetch and memory read, of course they are very similar to each other. The only difference is that in the opcode fetch, since it's an instruction, so along with fetching you have to decode and execute it, so that is done in the last clock period T4. Okay, but once it is a memory read operation itself only, it is not a opcode fetch, so it is executed in 3T states only. Okay, so this is what is called, these are what is called as machine cycles. Okay, so opcode fetch is one machine cycle M1, memory read is another machine cycle M2. So machine cycles, they are basically generated from the clock cycles. So you have T states. So T states, they are nothing but the clock time period. So one clock period is called as one T states. Okay, so when you combine the T states, so many T states, they combine to form a machine cycle. Okay, and M cycles, machine cycles, and many machine cycles, they combine to form a instruction cycle. So instruction cycle is the time required for the complete execution of the instruction. Okay, so each instruction cycle has one or more than one machine cycle, and each machine cycle itself has one more than many T states or many clock periods are required. Okay, so like in this case, we have instruction, this complete is instruction cycle now from here to here. Okay, That is the total time that is required to execute this entire instruction. So it is opcode fetch along with the memory read. So opcode fetch is basically one machine cycle. Memory read is another machine cycle. So by machine cycle, what we mean that once you fetch a byte, okay, the time required to fetch a single byte from the memory, or if it's the right operation, that time required to read the data into the memory. So it may be instruction or data. That is basically one machine cycle. Okay, so one 8-bit data basically. If you handle one 8-bit data, to handle one 8-bit data at a time, so many time is required. That is a machine cycle. And many machine cycles they constitute their instruction cycle. So instruction cycle gives you the complete time that is required for the execution of instruction. Now see, if you see how much time is required for the execution of this instruction MVI A, 32H. Okay, so this instruction has two machine cycles. It needs 7 clock periods or 70 states, and depending upon the clock frequency, now you whatever you have. So if you again your clock, if your frequency of the clock is 2 megahertz, so your time period is 0.5 microseconds. So time required for execution is 0.5 into 7 microseconds. Okay, so this is how, once you know the t states for any machine cycle, sorry, for an instruction, you can simply compute how much time will be required to execute that instruction depending upon the clock frequency. Okay, so if the clock frequency is 3 megahertz, this time of course will be different, execution time. Okay, so this is why, because the processors they execute these instructions in microseconds, or if you have a more advanced processor, it may be even, they may take even less time in the nanoseconds. Okay, so when you see from the outside world, you see that okay, the entire instruction is being executed at once, but it is not like the case. Okay, so all the instructions they are fetched, decoded, and executed in a sequence by the processor. So one byte at a time. So if it is a 2-byte instruction, so the first byte will be opcode, the second byte will be data, right? So if it is 1-byte instruction, of course, opcode is the only byte that carries all the information recording the entire instruction. Okay, so in that case, you just need 40 states to complete the execution of that instruction, right? So there may be 3-byte instructions also. As an example, similarly, if it is a memory, so you have discussed memory read. So memory write, now that I will not explain because it is very similar to memory read. The only difference is that in place of generating the control signal that is read, the processor will activate write signal. Okay, so it also requires 3 t states, 3 clock periods. In the first clock period, the address is latched by the ALE. In the next 2 clock periods, your write signal is activated. Now whatever is the data on the data bus, it will be placed inside the memory. Okay, so I hope it is clear, otherwise I will draw it very short. This is first clock period. Sorry. Anyhow, forget this, some timing errors. So if it's a memory read write operation, so you need 3 clock cycles enough for memory write. Okay, so what you need, address bus will be placed, address will be placed on the address bus. Of course, the higher and the lower address is 80 to 87, then 8 to 15. So you place higher order address here, it stays here for the 3 cycles, and the lower order address on the lower 8 bits. During the first clock's period itself, your ALE will get activated. It goes from 0 to 1, address is latched, and since it's memory operation, again IO oblique memory, it will be at logic 0. And now in place of generating this read signal, you have to activate the write signal. Okay, so the write signal will be activated at what? It will go from 1 to 0 in the second clock. and then it will be again turned to 1 by the processor. Okay, so during this time, whatever is the, now see, initially when the memory read operation, what was there, the data from the memory was going on the data bus, and then from the data bus it goes inside the processor. So if it's a memory write operation, there is already data on the data bus. Okay, the processor has already placed the bus and data on the data bus. So once this write signal gets activated, so this data bus will go from memory and this data bus to the memory. So again it is done in the T3. So you need again 3 clock periods for this memory write as well. Okay, so opcode fetch, it requires 40 states. Memory read, it requires 3 T states, and memory write operation, it also requires 3 states. Okay, but see, and you can see there is no one-to-one dependence between the number of bytes and the machine cycles that are executed. Let us suppose I take one more example before you conclude it. You have an instruction, and the instruction is suppose, of course we have not discussed about the instructions. Okay, I'm just taking the examples. You have instruction sta 2065H. This is a 3-byte instruction. Okay, what is the purpose of this instruction? The purpose of this is store accumulator, basically ST for store accumulator. It means you have to store the contents of register A or accumulator into memory location that is specified in this 16-bit address, that is 2065H. This is instruction. Okay, you have to copy the contents of accumulator into memory location, the address of which is specified here. So it can be any address. Okay, now you see, you can see that it is a 3-byte instruction because you need first byte, that will be of course opcode. So the opcode for this is 32H, and the second 2 bytes they now carry the address. Okay, if in the last case it was MVI A, 32, so the first byte was opcode, the second byte was data. Now in this case the first byte is opcode, this next 2 bytes they are the address of the memory location, they are not data basically. And see, there is a, whenever you store this memory address in the address of the memory in the memory location, so we store it like this. So 65H first followed by 20H. This is standard procedure. Okay, higher lower order address first followed by higher order address first. Okay, I will not draw the entire timing diagram, but I will just see how many T states will be required to get this. So what the processor will do, it will first fetch this operation code from some memory location. So that memory location can be anything. Suppose it is stored as 2050H. The next is stored at 2151. The next is stored at 2052H. So these are 3 memory locations at which the opcode and the operand both are saved. Okay, so this is now operand basically, these 2 bytes. This is your operation code. What the processor is going to do, it will first fetch the opcode, decode it and execute it. It will come to know that okay, it has to store the contents of accumulator into a memory location, the address of which is specified in the next 2 locations, right? So first is your opcode fetch, of course. So it requires 40 states. Okay, that is clear to you. What is the second operation here? The second operation will be memory read, because you have to read this 65H from the memory. Okay, second address your operation is memory read, and it requires 3 T states. What will be third? It will be again memory read, because you have to read 2 bytes. Okay, of course these 2 bytes they are address, they are not data. Okay, but you need 2 memory read cycles. So it again requires 3 T states. So is the instruction completed? No, because we have to move the contents of A into that memory location. It means we have another machine cycle which will be memory write cycle, which again requires 3 T states. Okay, so total we have 4 machine cycles for this. Out of which one first is opcode fetch, second is memory read, third is memory read, fourth is memory write. And how many T states will be required now? 4 plus 3 plus 3 plus 3. So you need 13 T states. So this instruction requires 13 T states and 4 machine cycles for execution. I will just go through briefly how the processor will do all this in a sequence. Okay, what it will do first, in the first opcode fetch, now that is okay, it will place 2020h higher order address on A15 to A8. Lower order address, that is 50h, will be placed on A7 or AD7 to AD0. So in the first clock signal, your ALE will get activated. It will go from 0 to 1. Your address is latched, right? And at the same time, your input output oblique memory status signal, it will be set to 0. And in the second clock signal, now the read signal will be activated. It will go from 1 to 0. Okay, and during next 2 cycles, now this opcode will go from the memory into the data bus. It will come inside the processor. In the T4 last cycle, it will be decoded. Okay, of course the instruction is not executed now because it has to do some other operations now. So this is one part, that is opcode fetch. Now what the processor will do in the next cycle, which is the memory read cycle? It has to fetch a byte 65h from the memory, which is 2051h. So by the time the first instruction is being fetched and decoded, the program counter contents has already been incremented by 1 to 2051h. Now the processor will place this address 250. This is first part. In the second part, the processor will place now 20h on the higher 8 bits, that is A15 to A8. Lower address, that is 51h on AD7 to AD0. Again, it will activate ALE signal and set this control signal, that is read. So this byte 65h will go from the memory into the your processor. Okay, similarly in the third cycle, 20h will come from the memory into the processor, and the address on now buses will be given from this 2052h, and the control signal will be generated in the same way. Okay, now what the processor will do, now this instruction was completed. It has fetched the instruction code, okay, decoded it, then it has seen that it has to store the contents of A into some memory location whose address is 2065h. So that address is just fetched from the memory in the next 2 machine cycles. The data has not been written yet. Okay, so in the last cycle, so 2 and 3 they are same. Okay, in the last part, in the 4th machine cycle, which is a memory write cycle, now what the processor will do, okay, it has to place the address, the contents of accumulator on this address. It means on your address bus, that is A15 to A8 and your AD7 to AD0, you have to store or place the address of the memory location, that is 20 on this and 65 on this. Okay, so the processor has first in the 2 machine cycle this fetch this instruction, this address. Of course it has to be stored somewhere in this processor, and in the last machine cycle, now this memory location has to be identified 2065h. Now since this address is already fetched from the memory, so this address has to be placed on the address bus. Okay, so it will place the higher order address and the lower order address. Again, we will activate ALE to enable this latch and to latch this lower order 8 bytes so that it can be used for data. And in the next cycle, now it will generate a write signal. Okay, so the data on the accumulator which is now placed on the data bus. Okay, so when the signal gets activated, so that data from the accumulator will go to the memory location, which is identified by this address. Okay, this is how it is executed. So you can, so at your own place, you can draw the timing diagrams for this. Okay, so you now know what are the various parts. You just have to combine them. So code fetch 2 machine cycles for read and 1 machine cycle for write. Your execution is done. Okay, now see, so this is what I was trying to say, that although it is a 3 byte instruction, okay, so but for in this 3 byte instruction you need 4 machine cycles. Okay, so it is not like this, that okay, the number of machine cycles, they directly correspond to the number of bytes that are used in the instruction. It was of course true for the previous case when we have used this instruction move c comma a, which was a 1 byte or a single byte instruction, and we have seen that it has only one machine cycle, and that is opcode fetch. So the entire instruction is executed in this opcode fetch only. Then we have taken one more example, mvia comma 32h. So this is a 2 byte instruction, and of course you need 2 machine cycles. Okay, one is opcode fetch and one is memory read for this. But when you have this instruction sta2065h, of course it is a 3 byte instruction because you need one memory location for a code, the second 2 locations for the address. Okay, but if you see this number of machine cycles, so it has 4 machine cycles. Okay, it means the machine cycles, they are not directly related to the number of bytes, okay, that are used to store the instruction. So I hope this timing diagram concept is clear to you. So we will carry on with this the next class.